So welcome again, everybody. We'll continue about integrals. So the topic is to understand what does this mean. The integral of function f, when we think that, okay, f is a map from some abstract set S to the real numbers. And we assume that we are looking at the set, a sigma algebra on the set, and a measure on the sigma algebra. And to be able to work on this, so we of course assume that f is measurable with respect to the right things. So that means the abstract space sigma algebra is calligraphic, and then the Borel sigma algebra B. That's the setup. And let's recall what we already know. So we know that if f happens to be simple and positive, so recall that this means that the range of f is finite. This is what we use the word simple for, and then plus indicates that f is non-negative. In that case, we defined the integral of f to be a sum of the values of x in the range of f, x times the measure of the pre-image of this value under f. And that's what we denoted previously with some special sign, because that was the preliminary integral. So that was the sign that we used for this definition. But when we are extending, so then we actually will omit this sign, and we just say that, okay, in the special case that f turns out to be simple and positive, so then this integral means this sum. So this is was the elementary case. Then was the second case where f is m for measurable, and then anything that means measurable, and plus means still non-negative. Well, we assume here already that f is measurable, so then yeah, okay, that's there. So for non-negative, we defined what is the integral of f against some measure mu to be the supremum when we approximate from below. So now we can write g is less than f, and well, we are looking at the non-negative realm, and then we require g to be simple. And now we can just write the integral of g d mu here, because we recall that this box can be omitted for in the simple case. But okay, maybe I will put the box there. So now we recall that the box always mean a sum. So when I write the box, I mean that, okay, we have a simple function there, finite range. It means that boxes are actually sums. There's nothing to integrate in the infinitesimal sense here. And now, what about the case where f is a general measurable function? Then what should be the integral of f in this case? This is what we haven't yet seen, at least in the lectures. So what is actually happening here is that now we assume that f can have positive and negative values. So we need a little bit of care, because remember, mu can assign infinities. So this measure here of some set, this can be infinite. And if we have plus infinite and minus infinite, we will be in problems, okay, how to define things. So we need to be careful that we are not summing plus infinities and minus infinities. That's why actually this is not possible, unfortunately. So we are not able to integrate anything. In the positive realm, we are. So recall an important point that this integral here can take values. Okay, it's non-negative. Everything is non-negative in these sums and supremums. So then the supremum is also non-negative, but it can be infinite. And and the same is true, of course, in this case also for simple functions. So let's maybe write it down there. We remember this, so we can also make the point that this can be also between 0 and infinite, including infinite. So now when we have plus and minus signs in the f, so these approximating things can diverge, and we have this plus and minus infinity problem. So we are not going to define the integral for everything, but we restrict our domain a little bit. What is the good space of functions where we can integrate nicely? That space will be denoted by L1 of calligraphic S. This is defined as this is those measurable functions such that the integral of the absolute value of f is finite. Okay. Does this definition make sense here? If we have a measurable function and then we take the absolute value, so is that a measurable function still? Yes, it is, because the absolute value is a continuous map. So when we take the composition of measurable and continuous, we will get again a measurable function. So we know how to define this integral using this step 2. So so whenever you give me any measurable function, then I can check. I take the absolute value, I integrate that one, and I can check that, okay, is that in L1? If it is, then I will be able to define what I want to define. So, so these were the definitions in the previous cases, and now the third case for L1 functions. What is the definition? It's not complicated at all, actually. From now on, everything is simple. The previous lecture was demanding because the hard thing was to define and work on this supremum here. That was the difficult thing. Today's things will be actually quite easy. So what do? We take the positive part of f, we integrate that, and then we integrate the negative part of f, and then we calculate this difference here. And we need to define what is the positive part of f. So maybe you have seen that one before. The positive part of f is just the maximum of f and 0. And the negative part is we take the minimum of f and 0. So if you take minimum of f and 0, you get something negative or 0. So then we put the minus sign there in front. If I take a function f and I calculate this max of f and 0, I will do it pointwise for every value of f. So I will get the new function, which is again a measurable function, because again, the function that maps a number to the max of it and 0, that is a continuous function. So that's why f plus is a measurable function as well. And this function is a non-negative function. Yeah. So this integral is defined by this part 2 here. Yeah. F minus, this minus sign guarantees that this function is actually also a non-negative function. So the integral is well defined by part 2. Can these be infinities? No, because let's see, f plus is the positive sign. So it's the max of f and 0. So f is of course less than the absolute value of f. So then this max of f and 0 is at most the absolute value of f. Now we are comparing two functions which are both non-negative, f plus and absolute value. So these are both non-negative functions, so we can calculate the integrals. We know from previous lecture that the monotonicity of the integral that we proved carefully previously implies that the integral of f plus is less than the integral of the absolute value. And because f is defined to be in L1, so then that's why this absolute value integral is a finite number. And we learned that this f plus integral is a non-negative and finite. The same is true for f minus. So if you look at f minus, we have this, and in the same way, this is at least the minus of the absolute value. So this is also that way. And again, the monotonicity implies that that's a non-negative function. So we get the same conclusion that also f minus is a finite number, non-negative. Do you have questions about these conclusions? Does it appear clear enough? Very good, because it's time to erase a bit and make space for new things. So an important point to make. We have a finite number here. This is a finite real number. This is a finite real number here as well. And I take the difference. So in this case, the L1 integral takes values as a proper real number. Sorry, it can be, of course, negative number as well. So, or maybe we can write it in this way. It takes values strictly bigger than minus infinity, strictly less than plus infinity. This way, based on what we just reasoned here. So, and that's an important difference. It's not a big thing, but it's an important detail that these values can take infinities, and then our integration theory for positive functions works with infinities well. Our integration theory for signed functions needs to work in the finite realm so that we avoid these infinities, plus and minus infinities. Okay. Do you have any questions about this one? Not so far. One more definition. If f is in either positive and measurable, or if f is in L1, yes. Note also that these two classes, none of them is bigger than the other. So there are functions which are here, but not there. There are functions which are here, but not there. So, but anyway, in this case, if f is either there or there, so then we can ask, okay, what should we define if we want to integrate over some set? What should be the definition of this one? That's something that we haven't yet done, right? Let's do it now, because that's very, very simple. We define it to be the integral of f times the indicator of the set that we are looking at. That's the definition for yeah, that's the most general definition that we will look at. Yeah. Okay. Especially, yeah, sometimes we write the full space there if you like. So we can write the integral in this sense that we did already. Or let me clean this one up. Okay, so sorry, now the Microsoft is giving a bit of a problem. Let's see. Let's wait a bit for this program to sync. It's syncing badly with the cloud service apparently. Anyway, Is the page broken? It's a bit broken. So let's see what I wanted to say. I wanted to say that sometimes we write for this integral that we have here, we might write here the symbol S to emphasize that, okay, we are integrating. The space where we are integrating is the full space, or we might write it there as well to emphasize that for the non-negative function, we integrate over the full space. These were now the full definitions for integrals. In the same way, you can extend things for vector valued and complex valued, but let's not worry about those now. This is the important definition. Yes. Let me think. What are the key facts about, well, this extension? So first of all, this map from f to the integral of f d mu, where we assume that we are now mapping a function in L1. That means, okay, these functions have a name. Such functions are called integrable functions. So if we map an integrable function from the L1 space, so now it's a mapping from the L1 space to the set of real numbers. Yeah. So this map is again a functional. Now it's signed functional because it can take negative values. So the basic fact is that this functional is linear and monotone in the same way as the previous integrals. And again, we can ask, okay, there should be some kind of inheritance. Well, now the inheritance is really, really trivial to prove, because why is that? Well, because this definition of the signed integral is defined using linearity. So when you have linearity here, so then the linearity is immediately inherited to the signed integrals as well. Monotonicity is also rather trivial to check, so I think we should not spend time on those, unless you have questions. Do you have questions here? Give me green light if this happens. Seems to be clear enough, or who thinks that this is kind of understandable? I want to see at least 5 green lights. Okay, I got 5, but maybe I want to see at least 10 green lights. I have 9, 10. That's it. That's enough. Let's do with 10. And I don't see any red lights, so then I take it as interpretation that you might not have immediate questions. Thanks for your inputs. It's time to move on. Let's open a new page, and let's hope that yeah, this whiteboard works. Another fact. One fact about signed integrals is that let's see, how should we write it? Let's write it in this way. For any f, which is an integrable function, possibly signed function, what can we say about the absolute value of the integral? Now we know that we can do this. Maybe I should actually mention, this is maybe a not very good notation. What's wrong with this notation actually? I mean, people use this notation, but there's something wrong in this notation. If I write L1S, can you recognize what's bad with this notation? The bad thing is that, okay, whether or not f is integrable, it's not the property of the sigma algebra. It's a property of f and the measure as well. So actually we should write there L1 with respect to the measure. Yeah, because assume that you change the measure, so then this integrability might disappear. For some measures, f may be integrable. From some other measures, mu, it may not be integrable. For example, think about the measure defined by mu is equal to 0 identically. Is that the measure? It is a measure because the measure of the empty set is, if you look at the measure of the empty set is 0 as it should be. Is it countably additive? Well, when you add zeros, you always get zeros, so it's countably additive as well. So actually this is a measure, and for this measure everything is integrable, of course. So yes, the L1 for the 0 measure is trivially contains all the measurable functions, but for relevant measures, so then the f in L1 mu means that the absolute value should be integrated into a finite number. And this is a fact. So if you take any f in the L1 mu, so then the absolute value of the integral is less than the integral of the absolute value. This is not very deep theorem because it's so easy to prove, but it's extremely useful in analysis and application. So let's see how to prove this one. Let's look. Okay, how do we calculate? What was the definition of this thing? By definition, we remember it was defined as the f plus integral minus the f minus integral. Then we look at the absolute values of it. So now we remember this is just an ordinary real number. This is an ordinary real number. So we use the triangle inequality. These are non-negative numbers as well. So well, we can always do the triangle inequality in this way. And then here, and then we remember that these are non-negative functions. We take the non-negative integral. So we can take away the absolute values, and we have here just these things, and then we use the linearity of the positive integrals. That was, remember, it was very hard to prove this one, but now we have that. We use that very deep theorem that the positive integral of any positive measurable functions is a linear functional here, so we can write these inside the integrals. And now if you look at what is f plus plus f minus, so then with a bit of thinking, you might recognize that, aha, f plus plus f minus, if f happens to be positive valued, so then this value gives the f itself and this gives 0. If the value of f is negative, so then this one gives the minus of f and this one gives nothing. So actually at every point, this value is actually equal to the absolute value of f. And that's why what we are looking here is actually just the integral of the absolute value of f. And here is that crucial inequality sign, the triangle inequality of the ordinary real number. So that's the proof. Do you have questions?